So all a polynomial or rational inequality is it's asking you where is the graph above or below the x-axis. So if I was going to sketch a random polynomial function, how would I graph a quadratic function and maybe a linear function? Those are both polynomials. And how about I graph a couple rational functions? So one rational function we've been looking at kind of looks like this, right? Another rational function, if it had maybe a slant asymptote, I don't want to do a slant asymptote. How about just a different rational function that might go through the x-axis, something like that, right? So polynomial functions, rational functions, we kind of know what they look like. Where do each of those functions change sign? So where do they change from positives to negatives? So these are all positive y values. These are all negative y values. Where did the graph change sign? It changes sign at the x-intercepts for polynomial functions, and it changes sign also at x-intercepts for rational functions, but also at asymptotes. So all of these y values were positive, jump the asymptote, now all these y values are negative down here. So I wrote a little bit about continuous functions because in calculus you're going to talk about continuous functions. They have no breaks in the graph. So if a function is continuous, it'll cross the x-axis where it has odd multiplicity. We know that. This is important in polynomial inequalities because when it crosses the x-axis, it changes sign. So x-intercepts are key points on the graph. And breaks in the graph also occur at vertical asymptotes. So it can go from, positive infinity down to negative infinity across the asymptote. So in bold, I just wrote the moral of the story is we should always check our x-intercepts and our vertical asymptotes when we're trying to figure out when an inequality is changing sign from positive to negative. And we always want the inequality to have 0 on one side of it, because then I'm looking for positives or negatives. If the inequality has the number 4 on one side of it, I can't use that rule of positive to negative. So we're going to have to add or subtract terms to both sides. And I do that on the back page, so you'll see an example of that. So the idea is just we're going to use x-intercepts and vertical asymptotes as our critical numbers. So the critical numbers are x-intercepts and vertical asymptotes, because it's where the graph is going to change sign from positive to negative. So the test intervals are in between the critical values. So this is more like algebraic. If I just looked at this graph right now, so if I look at the graph in my calculator before I do any kind of algebra work, so I'm going to plug in x squared minus 2x minus 3. So plugging it into my y equals menu, I'm just going to look at the graph and see if I can see where is this graph positive or negative. Well, the graph is negative right here, right? So where is this function below 0 for my y values? Right here, right? Between, it looks like -1 on the x-axis and +3 on the x-axis. So from the graph, you can answer inequalities. So you don't need the algebra if you could look at the graphing calculator. So I might ask it on a calculator or a non-calculator section. So the algebraic steps I'm going to show you here are when you can't just look at the graph. I already know the answer for this question. X is between -1 and +3. So how do I get there if I don't have the graph in front of me? I just have an equation. So you ask yourself, where are the x-intercepts? So x-intercepts you get by factoring, right? X, what would this be? -3 and +1 for my factors. So my x-intercepts, we said, are at 3 or -1. I got that from the graph, but I might have to be able to solve that algebraically. That's the point of why we studied polynomial functions first. So when it says your test intervals, I'm just plotting on a number line, -1 and +3. Those would be the breaks in the x-axis. right, where the graph might change sign, positive to negative. I'm using open circles because it says strictly less than 0. So I don't want to include -1. Whoops. I don't want to include -1 because at -1, the graph equals 0. So I just use open circles to show that it's a strictly less than symbol. So now it says test a number in each of your intervals and shade where the correct solution region is. So a number that would fall to the left of -1 would be like -2. A number that would fall in between these x values, I just usually pick 0. And a number that would fall to the right of +3 would be like +4. So algebraically, all you're doing is plugging the x value into the quadratic function to see if it comes out as a positive or a negative value. So here's where you've got to do some algebra without a calculator, or if you did have the calculator, you could just go to your table and just see, what happens at -2. So when I plug in -2, I actually get 5 because I've got +4 plus 4, right? 4 plus 4 is 8, minus 3 is 5. So this came out +5. Did I want a positive value? No, I wanted it to be less than 0. So that solution region failed my test. If I plug in 0 into the original inequality, I just get -3, and -3 is less than 0. So that test point worked. And if I plug in 4, I would get, 16 minus 11, right? Because this would be -8 and minus an additional 3. So I'd get +5. So +5 fails because it came out positive, not negative. So my solution region is exactly what the graph already told me, but it's from -1 up to +3. So this is just a little bit more complicated algebra to get exactly what the graph already told you. Where is the graph below the x-axis? So you might need to figure out what those critical points are, but you could either do it by hand or with a calculator if it was on a calculator section. So you're finding your test points, testing values in the inequality, and then just concluding where did it come out negative only in this region. So between -1 and 3 on the x-axis. So I just want to do one more example with you, and then I left 3 and 4 for you to kind of do with the video because I figured you could do that on your own time if you had to do the retake. But I wanted to show you a rational function and how that's different than the polynomial function. So just to give you a preview, we kind of already know what the answer is going to be. If I look at the graph, so kind of ruin the surprise here, but a rational function is just dipping below the x-axis here and it's above the x-axis here. What does it want to know? When it's less than or equal to 0. Well, it's already kind of right there. So all I have to figure out is what critical point, so where does x start below the x-axis? I don't want this part, I don't want this part over here. So this step is just helping you figure out where it's below the x-axis. Let's see, where would my zeros and vertical asymptotes occur? It looks like I have a 0 at 0, right? Because 2 times 0 is 0. And I have a vertical asymptote at 5. So this graph is changing signs at 0 and at 5. I can kind of see that on my graph. So determine my test intervals. So here's one a little bit tricky thing. See how this says less than or equal to 0? I can include my x-intercept because at 0, the graph is at 0, but I can't include my vertical asymptote because the graph never touches the vertical asymptote. So what I'm going to do is use a filled-in circle at 0 on the number line, but an open circle at 5, right? Because that was a vertical asymptote and that was an x-intercept. So because this was greater than or equal to 0, I can use a filled-in circle. But for asymptotes, you always use open circles. And I think that difference is challenging for students. Like, why can't I just use 2 filled in circles? Your function will never equal 5. But your function is okay to equal the x-intercept. Because of this, it could be less than or equal to 0 in the original inequality. If you set this up correctly, it makes it a lot easier to write your inequality at the end. So I just make sure I've got my filled in or open circles correct based on the inequality. On the previous page, they were both open circles because it said strictly less than 0, so I could not include my x-intercepts. So you can always include your x-intercepts, but you can never include your asymptotes on this one. So I'm going to plug in the points -1, +1, and +6, and see what I get up here. So if I plug in -1, I'm going to get -2 over -6, which is +1/3. +1/3 is not less than 0. So 1/3 fails. If I plug in +1, I get 2 over -4, right? And 2 over -4 is -1/2. So that region works. I already know that region's going to work because I kind of cheated and looked at the graph, right? So I knew that this region was below the x-axis. So that should make sense. If I plug in 6, I would get 12 over 1 is 12. So that's a positive value. So 6 also fails because I want negative values. So my solution region is between 0 and 5 on the x-axis. 0 is less than or equal to x, which is strictly less than 5. And I can see that that is where my graph is below the x-axis. So it should all kind of go hand in hand with practicing things about rational functions and polynomial functions and looking at a graph, where is it above or below the x-axis. So when you do example 3 using the video or on your own, now you're looking for where is this function above the x-axis because it says greater than 0. So when we come back in, you can use the video, or you could just try them on your own and I could come around and check them for you. But you're going to do 3 and 4, and then you're also going to do the application problems. So probably the video is just for